Welcome to our first video for week 8. This video is on combinational circuit analysis. Now let's start with the basics. In order to analyze a combinational logic circuit, the first thing that you need is a formal description of the logic function in the form of a Boolean expression that can be then manipulated in order to obtain a sum of products. And then you can take this sum of products and directly implement a programmable logic array. Now, what is actually a programmable logic array? Well, it is a type of a logic device which is meant to implement combinational logic circuits. It looks like this. Its main feature is that it is composed by a set of AND gates, like the ones that you see here, which link to a set of programmable OR gates, the ones that you see here. Now, if you want to have n input variables, you will need 2 in the power of n AND gates. And if you want to have m outputs from this PLA, then there should be m OR gates. As we've mentioned multiple times, a truth table can be implemented with a memory device. The only thing that you need is to use the right number of input addresses, starting from the first row up until the last row, and input the storage data, which stands for the value of the truth table that represents this particular address over here. Now that is straightforward. In this lecture, we will start with a given combinational circuit, which is composed of a set of logic gates, and then we're going to go through the next 3 steps. The first one is to deduce the Boolean expression of its logic function. After we do that, we will deduce the truth table, and then we are going to conclude with a few tricks to simplify it or to reproduce it with different set of logic gates. Let's now consider the following logic circuit. Take a moment to pause the video and check the circuit. Now let's see how you can extract the truth table. It is quite an easy process. So check out what we've done here. If you read the values vertically of the 3 inputs, then you will realize that the first input is 0, 0, 0. The second one is 0, 0, 1, which stands for number 1 in decimal. Then you got 0, 1, 0, which stands for 2. And as you read them all, you will go through all the numbers from 0, 1, 2, then 3, and all the way to 7, which is in binary 1, 1, 1. So these are all the possible combinations of input you can give. Now, as a small trick, in order to make this process safely and very, very fast, you can start with the first variable where half of them are zeros and then the other half are ones. Now, we need 8 different values here because you got 3 input variables, so this means 2 in the power of 3 inputs. So you got the 4 first being zeros and then the other 4 being ones. When you go to the next variable, well, the remaining combinations are for 2 variables, so this actually gives you 2 in the power of 2 combinations. So for these 4 bits, the first half, these 2, you make them 0, and the other 2, you make them 1. And then you repeat again, 0, 0, 1, 1. And for the last variable, you got only one option, which means 2 in the power of 1, 2 options. So you concentrate to the first 2 values. Half of them being 0 means the first one is 0, and the other one is 1. So this means that you repeat the pattern 0, 1, 0, 1, 0, 1, up until you have 8 different inputs. And then it's straightforward. You just follow the rules of the gates. You have to be really careful, and then you will end up all the way over the end of the logic circuit to the output of the function. So it's that easy. After you do this process, you have all of the rows. So each row over here is like vertically reading the inputs. Like if I randomly pick the sixth row, which is row 5, the input should be the number 5, of course. It's the one over here. And if you go over here, you will realize that the output should be 1. So that is a very easy way to approach a logic circuit and extract the truth table. Now that you do have the truth table, what you know from the previous lectures is that you can convert that to a sum of products or a product of sums. To do so, you need the min terms and the max terms respectively. And as you should remember, the process is quite easy. If this is the canonical sum of products, you know that it's extracted by focusing on these rows for which the function output is 1. Remember that if the value of the input variable is 1, then you use the variable as is. If there is a 0, just like here for instance, then you need to use a dash. The process is straightforward. It leads to this function over here. If you use the max terms, then you will end up with the product of sums, which is the equivalent of the sum of products, as you know, and this is how you symbolize the canonical form of it. Now, if this is the function that you get by having the sum of products, then with the usual tricks that you have learned in previous lectures, you will end up in something which is minimized. Now, quickly going through each and every line here that you have. Well, we first identify that we got a y dash and a y here, and that the common factors are x times z. So that leaves us here with y dash or y, which, as you know, gives us a result always 1. Now, in the third line, to make things more clear and more convenient, we move xz to the second position here. Now, the next step is as follows. We will identify z as the common factor here. So in the next line, you got x dash times y dash, or x, and all of this times z. Logical OR here, x dash, y times z dash. Now, by using the dual of distributivity, you get this one over here. In case you're wondering how you should remember that, well, you have to use your experience with practicing. If you go and check how the dual distributivity works, you will soon realize that you can convert these x dash times y or x to x or x dash, which you have here, and x or y dash. Now, as you understand, this is pretty convenient because, again, we got an x or x, and as you know, this is coming from the basic operations, and it's called a complement operation, which gives you always 1. So you end up in this format over here, this form of a function over here, which is the most simplified you can come up with. However, there is an even more convenient way. You can use the circuit and just note down with each level that you cross the variables, like you see that y here goes through a NOT gate, so it becomes y dash. Then it goes through an OR gate, so it's y dash or something else, and that something else is an x. And so forth up until you get to the end, to the final gate. So after 1, 2, 3 levels, and by ignoring the NOT gates here, you will end up to the final function over here, which, as you can see, coincides with the simplified form that we have here after we've done some mathematical operations, Boolean algebraic operations, starting from the sum of products. So the simplified format, as you would expect, coincides with what you got here after you note all the results from the gates on the circuit, which is more or less like a linear process. You linearly cross from one level to the next. Now, what is important to say at this stage is that if you do this linear algebraic process and you end up with a simplified form of the function, you can always further multiply in order to reobtain the sum of products. And if you do this, you will end up in a sum of some products, although somebody may say that you're missing the products of 3 variables. Well, let's take xz as our example over here. Well, this obviously represents xz y dash and xz y. So if you're having 2 variables and you're missing the third, this means that it implies you're using twice this couple over here, once with the other variable and another time with its complement. And if you think the other way around, if you have them, if you have these terms here, including the complement, again, by using the simple operations that you should be aware of by now, you realize that you can get rid of the y dash. So you would end up in this xz format over here. Now, doing things a little bit different, the function that you have here, the simplified, can be further added out to reobtain this time the product of sums. Just check out the mathematical operations. We take x or y dash. You do this once for x dash, then you do it again for y dash, sorry, for y, and then for z dash. So for the first time that you did this plus this, you end up with this term. The second, adding out between this and y, you get this term over here, times the third adding that you do between this couple over here and z dash, and so forth. You do the same thing for z. With x dash, z with y, and z with z dash. But as you can see, you can simplify things over here, because obviously, if you have x or x dash, the result will be 1. So 1 or y dash gives you 1 for sure. The same applies also here. And z or z dash, of course, gives you 1 again. These are complements. Now, if this is your product of sums and a simplified one, as you can see, then you can extract a 2-level OR AND circuit. First level is the level of ORs here, and then the final one is the AND gate at the end of the function. So why do we bother so much about the sum of products and the product of sums? Well, the answer lies here. Transforming any combinational logic circuit to a sum of products or a product of sums has 2 main advantages. The first one is that it ensures that the delay between the input and the output signal, in other words from here up until here, is always known. If you think of it, because it is a sum of products, or equivalently a product of sums, you have only 2 levels. So using the sum of products as we do here, and by ignoring the NOT gates, you see that you have a sum, which is the final level, preceded by AND operations. So it's the sum of logical products. You always have a 2-time delay to count for whatever is the number of gates. Now in this example, the number of gates is what you see over here, 3 gates for the first level and always 1 gate for the final level. If this is the first, let's say, component of the time delay, and that will be the second one, if you put everything down on, let's say, something like a chart of time, you see that you spend 1 time unit for the inputs to go through the AND gates, and a final level for the final OR, because it's a sum of products, for the final delay component. Furthermore, if you choose to minimize the sum of products or the product of sums, what you achieve, well, it is to have the same time delay, because you do not change that. You cannot change that. It will always have to go in parallel through one level in a second. However, what you do is that you can reduce the overall circuit size. So if we're talking about a sum of products, by minimizing it, you may reduce the number of AND gates. This is not going to reduce the T1 component that you see here in the time. Nevertheless, it's going to reduce the cost because you reduced the circuit size. And as you can understand, especially for very complex circuits, this is very important. It does reduce the cost significantly. So getting almost to the end of this video, we're going to prove this time that every function that you're given, you can rewrite it, or the equivalent anyways circuit, you can reconfigure it so that it includes only NAND gates. Suppose that you're given a sum of products, and we're going to use this sum of products as our example. You can always rewrite it with NAND gates. There's a simple thing we need to remember. If this is a NAND gate, because of De Morgan, it can be written by having an OR gate and negating all of its inputs. So essentially this is another symbol for a NAND gate. Now, because of involution, if you use the negation twice, you do not change the essence of the circuit. However, what you do achieve is to have a negation to all the inputs of this OR. So you ended up essentially with a NAND gate, as we proved here. And at the same time, for the first level of the AND gates, you have converted that to NAND gates. And this is how we prove with a simple example that you can, of course, generalize that every function can be rewritten with using only NAND. And of course, we can use the same logic approach to proving that you can rewrite everything using only NOR gates. This time we're going to use the product of sums. So this is an example of product of sums. Again, by using De Morgan, a NOR gate is equivalent to this symbol over here that uses an AND gate with all of its inputs negated. So essentially this is again another symbol for the NOR gate. And just like we did previously for proving the NAND gates, we're going to get advantage of involution. And therefore we achieve to have on the first level OR gates negated at the end, so this is an OR, and an AND gate with inputs which are negated, which is essentially, as we know from De Morgan, again an OR. And that's the proof that you can convert everything to a circuit that includes only NOR gates. And with that, we reach at the end of this video.